Good morning, everyone. So my talk today is on the measurements of ion outflow from the Earth's ionosphere. And before I start, I'd like to thank Rick for his kind invitation for me to give this talk. And excuse me. And as you have heard from both Peter and Jim earlier, the topic of ion outflow kind of was not as old as the first Chapman conference. And in fact, looking back, at the time of the first Chapman conference, our perception of Magnetosphere-Ionosphere coupling was primarily a kind of a one-way street. In other words, a coupling that was dominated by transfer of mass, momentum, and energy from the magnetosphere to the ionosphere. But at the time, this perception at the time was kind of turned on its head, so to speak, by the work of Dick Sharp, S. Shirley, and the colleagues at Lockheed at the time, where they discovered the presence of energetic oxygen ions originating from the ionosphere right in the magnetosphere. And I think it's probably fair to say that Shirley and Sharp et al.'s work not only have changed and helped change our perception of MI coupling to what it is now, but they also shaped a lot of work on ion outflows that has been done in the last few decades. So in my talk today, I will focus on the source region, the source populations, and also the variability of the various types of ion outflow populations. And such outflow populations can be categorized into two categories, namely thermal outflows, particularly the aerobic outflow and the polar wind, and also superthermal outflows, including things like ion beams, ion conics, and upwelling ions. Now, there have been several satellite observations and radar observations in the last 4 to 4.5 decades on ion outflows. And some of those were focused on the thermal outflows, i.e. polar wind and aerobic flow, including the observations, very early observations on Alouette 1 satellite and Explorer 31, and of course also the DE2, and also the observations from ISCAT and the ISCAT smart radar more recently. There are some other observations that were confined to the superthermal components, observations of beams, conics, and transverse ions, and so on. Notably, the S33 early on in the 870s by the Lockheed Group, as well as the Viking satellite and Freya satellite, and more recently the FAR satellite. And then there are also many more observations, the observation data sets that cover both the thermal and superthermal component, including the observations on the early ISIS-2 satellites, where, in fact, the transverse accelerated ions, or TAIs, were first reported by Kumpler and co-workers. And then in the 80s, DE1, and then later on Akebono, and more recently Polar, as well as a cluster. And as a matter of fact, the most recent observations of co-ions on cluster are particularly significant in terms of our understanding of the important role of co-ions and in the magnetosphere. I believe the next speaker would speak on that. So to start my presentation, this is kind of a schematic summary of the different the thermal and superthermal outflow populations and the kind of when and where they occur. and this includes the aurora bulk flow, both on the day side and the night side aurora in the top side ionosphere. A polar wind immediately above the top side ionosphere in the polar cap, and going up in altitude, transversely accelerated ions, which become conics at high altitude, both on the day side and the night side, as well as upwelling ions that occur exclusively in the morning sector on the day side, and also ion beams primarily in the so-called parallel acceleration altitude region. And then last but not least, the centrifugally accelerated polar wind ions in regions at high altitudes where the effect of centrifugal acceleration starts becoming important. Excuse me. So starting with aurora bulk flow, this slide shows the occurrence distribution of bulk upflow of oxygen ions observed at ISCAT in the 1980, from 1984 to 1996, so over a very long period of time. The three panels show the local time distribution at the 350, 400, and 500 kilometer altitude. And the distributions are shown, for upflow events that exceed a certain flux threshold in white, the events that exceed a certain velocity threshold in gray, as well as events that exceed both thresholds. As you can see, there is a gradual increase in the occurrence going up in altitude. And also the distribution at all three altitudes, the distribution peaks around pre-midnight. And the fact that the observed distribution peaks just before midnight simply is attributed to the fact that such ion outflow occurs both on the day side and on the night side, but B, that the fact that the ISCAT radar happens to be located close or right in the night side aurora zone, but with significantly equatorward of the day side aurora zone, and that's the reason why we have a sort of apparent peak in the night sector. Now this next slide now shows the data from the Svalbard radar, which is located at 75-degree invariant, which is kind of in the day side aurora zone. The four panels shows the local time distribution now of the ion flux, the average ion flux, at all Kp conditions, low Kp, medium Kp, and high Kp. And all four panels show that in this case, at Svalbard radar, the flux distribution actually peaks around magnetic noon instead of the pre-midnight. So once again, this reflects the fact that the upflow actually occurs on both the day side and the night side. However, the fact that the radar happens to be much closer to the day side aurora zone explains why there's an apparent peak in the observed distribution. Now, another interesting feature in here is that if you look at the distribution at very active times, there's actually the average flux over all the data samples actually have close to zero flux, and that reflects the fact that during active times, the peak ion outflow region is actually equatorward of the Svalbard radar, so that the Svalbard radar is seeing a lot of the ion outflows that have kind of returned back towards the ionosphere. And this next slide shows the yearly and quarterly the variations of the observed upflow, occurrence probability, average velocity, and the ion flux. The point of this slide is that there is very significant seasonal as well as long-term solar cycle variations in the ion outflow. And in particular, around the solar maximum, the ion flux is much greater, above a factor of 4 on average, greater than the ion flux at solar minimum. Okay. On the other hand, the velocity of the flow is actually smaller at solar max than at solar mean. And the higher ion flux at solar max is attributed to the fact that near solar maximum, the solar UV flux is stronger, and therefore the ionization density is also in the ionosphere is also higher. Now, on the other hand, at the same time, the velocity is also smaller because the neutral density is also higher, and therefore ion-neutral collision is more important at solar maximum, and therefore it's overall impedes the effective level of acceleration. Now, moving out to polar wind, now in the classical polar wind picture, somehow I prepared this presentation on a PC, but somehow it doesn't seem to. But that's okay. Anyway, the point is that in the classical polar wind picture, the polar wind it's primarily a steady state current-free flow in the polar ionosphere due to the presence of and bipolar electric field associated with the plasma pressure gradient along open field lines. However, in reality, the observed polar wind is neither the steady state nor the uniform and so on. And that's due to the fact that there are actually a number of so-called non-classical acceleration mechanisms in play. And that includes the parallel electric fields and plasma waves, particularly low frequency waves, which energize ions. Sorry. And it seems to be working funny. Anyway, and also there's also the effects of escaping the photoelectrons, which tend to enhance the strength of the ambipolar electric field. There's also the soft precipitating electrons and hot thermal electrons also contribute to enhancing the overall plasma pressure, and they also add up contribute to what Strong and co-workers termed generalized polar wind. And then last but not least, as I mentioned earlier, at high altitude, where the curvature of the magnetic field starts becoming important, then the convection electric field in such region can also lead to significant centrifugal acceleration. So this next slide compares the velocity of the various polar wind species on the day side and the night side. And qualitatively speaking, the day side and night side profiles are quite similar, certainly in terms of the velocity increase with altitude, and also in terms of the inverse mass dependence of the velocity. In other words, the lighter ions having a larger velocity than the heavier ions. And also in terms of the altitude region of the largest acceleration. On the other hand, quantitatively, there's clearly an asymmetry between the day side and the night side, sort of in favor of the day side, where the velocity is significantly higher. And how am I doing with time, Rick? Okay, good, thanks. So this next slide shows the local time distribution of the oxygen ion near the 1 RU altitude from Akibono. And as you can see, there is a day-night asymmetry. And also, then the velocity is generally in the order of 2 to 4 kilometers per second. I mentioned this number because this is just under the value of the ion escape velocity at this altitude, which is about 8 kilometers per second. So in other words, the polar wind and other thermal energy oxygen ions observed at this altitude cannot quite escape by itself unless it would acquire further ionization further at higher altitude. Okay. And I'll come back to this point shortly. And this next slide shows the observed polar wind occurrence distribution at near the polar apogee at 9 RE geocentric. Now these observations were from Xu et al. Taken near solar minimum. And it shows the hydrogen and oxygen density and velocity. The point in this slide is that even though these observations were made near solar maximum, the oxygen component was still quite observable in the polar wind, even though the density is, of course, significantly smaller than hydrogen. Then nevertheless, it was observed with a mean velocity of about 17 kilometers per second. In comparison, the hydrogen has a velocity on the order of about 45 kilometers per second. So that means that the two ions have a velocity ratio of about 2.7. Now, in comparison, if we apply the square root of inverse mass ratio, the ratio would be 4. So what that means then is that the observed ratio of velocity ratio is between unity and the square root mass ratio. And so the interpretation is that this intermediate value of velocity ratio probably is indicative of the fact that there may be more than one acceleration processes that contribute comparably to the overall energy gain. Okay, that's basically the interpretation. Now, an important and interesting aspect of thermal outflow is the variability of its composition. And certainly on DE1, on Akibono, and on polar, where there are capabilities to observe the composition of outflowing ions in detail, when sometimes observe molecular ions above 3,000 kilometer altitude, and also when also frequently observed quite variable ion composition ratio. And this the top panel in this slide shows an example from Craven et al. Of DE1 RIMS data during a magnetic storm in 1982, when molecular nitrogen, NO+, and molecular O2+ ions were all observed and quite clearly resolved. The bottom panel shows similar data from the Akibono satellite, where one can see that in this particular case, the N+ to O+ ratio is very close to unity. And then the molecular ion to oxygen ion ratio is 0.1. Now, the fact that the molecular ions are observed at such high altitude is very important because it tells us that the acceleration process, ion acceleration process, not only occurs at very, very low altitude, down to the top side and F region ionosphere, but that also the process is very fast, because otherwise there won't be enough time for the ions to get accelerated and then to get transported to high altitude. Okay, good. Now, so I'm going to speed up and to mention that I talked about the fact that the observed oxygen ions at 1 RE don't quite have enough energy to escape. However, they do have enough energy to get to a high altitude where the effect of centrifugal acceleration starts to take hold and to dominate over gravitation. And this is an example of a simulation showing how such ions can get energized sufficiently so that they can reach all the way to the magnetosphere. And in this case, for ions starting at 2 eV and 3 eV at 7,000 kilometers. Moving out quickly, to the energetic, the superthermal components. This is to show that in the case of ion conics, the one type of ion conics, namely restricted ion conics, typically start off at 3,000 kilometers and become energized up to about 100 eV by the time they get to about 9,000 kilometers. This is from Akebono data from Iyaki and co-workers. And on fast, the Strange-Way and co-workers have a very nice study showing the source of the energization of the ion conics by showing the correlation between the measured ion conic flux versus Ponting flux, electron number flux of solid electrons, as well as at real ELF amplitude. And the point of the correlation is that the correlation is certainly consistent with the picture of acceleration of the ion conics by broadband and faint waves, as well as the soft precipitating electrons contributing to the generating of ion outflow from the topside ionosphere underneath. This slide is just to show that, as I mentioned, the upwelling ions, which are also referred to as cleft ion fountain in the literature, tend to be observed exclusively in the morning sector, around 10 MLT, and they typically have the higher average energy and velocity. For example, in the case of oxygen, the order of 3 to 10 kilometers per second, even down at the 3,000 kilometer altitude. So they are clearly more energetic than the polar wind ions that I've shown earlier. I'm going to skip the details of the energetic ion outflow results because we have seen this before, but rather go straight to the sort of comparison between the thermal energy component, namely bulk upflow, and the superthermal ions, namely the upflowing ions. Now, admittedly, it's always tricky to compare thermal outflow at low altitude with superthermal outflow at high altitude. It's a little bit like comparing apples and oranges. But nevertheless, I'm going to do it anyway. And this is to show that on the one hand, the upflow flux is on the order of 2 times 10 to the 13 per square meter per second. In comparison, the energetic superthermal oxygen flux at DE1 altitude is about 8 times 10 to the 12. So in other words, in this, the average of the energetic component is less than 40% of the thermal component. So that tells us something about the relative relationship between the two components. And this is kind of a similar kind of sort of result by comparing the thermal outflow component observed on Akebono with the superthermal components observed both on DE1 at high altitude and also on polar at a lower altitude. The key point here is that there is significant acceleration of hydrogen between 9,000 and 16,000 kilometers, whereas in the case of oxygen, there is a clearly significant acceleration even below 9,000 kilometer altitude. So just to quickly summarize then, for the aerobe upflow and the polar wind, the source location and the strength and character clearly vary strongly with F10.7 and also with KP and also IMF. And both are frequently occurring, and in the case of the aerobe upflow, they are sort of too cold to escape. In contrast, ion beams and conics are much more energetic, and they don't occur all the time, but they do occur frequently enough. In fact, at more than half of the time, below 1 keV. And they also have quite diverse solar and magnetic activity dependencies. The one interesting aspect is that even though we try to look very hard for the return population, most of them actually do not return to the ionosphere, but rather remain in the magnetosphere, circulate around the magnetosphere, and presumably eventually escape from the magnetosphere. And certainly the oxygen, heavy oxygen ion component dominate the times at the times of high solar magnetic activity. The overall, I think the take-home message is that ion outflows do constitute an important response of the ionosphere thermosphere to the solar and magnetospheric energy input, and the overall population is constrained by the structure of the thermosphere and by the 11-year solar cycle. And there's clearly very significant variability in the composition, in the intensity, in the energy, and in the occurrences of the various populations. And the dominant populations being the aerobe upflow, the polar wind, and also the ion beam and conics. In terms of the acceleration mechanisms, certainly I think both parallel and perpendicular acceleration as well as centrifugal acceleration are all play an important, even critical role in the overall acceleration of the ion outflow. And the bottom line is that by now it's quite clear that the cold ionospheric ions are really the rule rather than the exception in the magnetosphere. Given the fact that there's a substantial fraction of the ions that are often hidden in the sunlit magnetosphere, which was recently demonstrated very nicely by some new recent results on cluster. Another important aspect is that is the potential influence of low cold oxygen ion flux that are sort of between the ionosphere and the plasma sheet, even during quiet times, and which may play an important role, or at least play a significant role in the overall dynamics of the magnetosphere during the less quiet times. Okay, thanks very much.
Are there any questions? Yes.
Regarding the ratio of velocity some nice work showing that if you had a hydrogen beam that was 4 times as energetic as or 4 times the velocity of an oxygen beam, you'd add a beam plasma instability that slow down hydrogen and increase oxygen. Do you think that's viable?
Probably, I guess the short answer is probably not in this case, because recall that the Bergman results apply to much more energetic ions, where this instability process it's a lot easier to kick in. But here we're talking about sort of quasi-thermal energy and velocity. Yeah.
I just wanted to say I feel like Rip Van Winkle after 40 years coming back to hearing the experimental results, which are outstanding. But I also wanted to correct 2 things in my own presentation that were very important. The first was how Chattanooga became able to measure everything in the world of this you're describing. It was due to Dr. Joe Dubnik here, who was the assistant to SRI in many ways, but defined the data processing, defined the experimental techniques, and basically set the way in motion for all of the ISCAT radars for what happened later. And Joe, I owe you a great vote of thanks for all that effort over many, many years. Secondly, there's a tendency, because of the name of polar wind, to think that it only happens at high latitudes. But I think it's pretty clear from the work of Don Carpenter that anytime you have a large-scale removal of plasmaspheric ions, that you have both subsonic and supersonic solutions. It's just how the cold plasma refills. And Don, that was very prescient. And I don't see Don right now. But, oh, there's Don. That was very prescient and really set in pace the later developments that owe a lot to you and your colleagues using the VLF Whistler techniques.
Great review, Andy. It occurred to me as you were talking and sort of separating the very low altitude radar ISCAT type measurements and what we've learned there in the bulk flow from the higher altitude stuff, that the transition region between those is really quite interesting. I'm thinking about the ISIS altitude measurements around 1,400 kilometers, where we're seeing, where we're not able to see the cold outflow because we didn't have the right instrumentation, but the transverse acceleration, the ions kicking up to a few electron volts, 10 up to 100 or even 200 eV. That's that transition between the two regions where the dynamic auroral processes are starting to take place.
Right.
Just a comment, actually.
Yeah. Okay. Good. Actually, if I can add to that, you're absolutely right. First of all, even though I keep referring to the sort of the TAI region to be sort of above the topside ionosphere, actually that's not completely true because during very active times, particularly during auroral substorms, you can see transverse ion acceleration all the way down to the topside ionosphere, 400, 500 kilometers. In fact, we probably hold the world record for the lowest altitude in one case, I believe. But in any case, the other point, though, is that it's clear that it's a combination of a number of factors, including the plasma density at the time and the amplitude of the amplitude currents and so on. So what I can say for certain, though, is that at least statistically, the acceleration region tends to be at a high transition altitude region tends to be at a high altitude on the day side and on the night side, and also it tends to be higher during solar maximum than solar minimum.
This might be a yes or no question.
Okay.
Do you think that the existence of a cold oxygen polar wind is evidence for oxygen getting out because of photoelectron or superthermal electron pulling as opposed to ion heating?
The answer is neither yes or no, but I don't know for sure. But seriously, I think both the sort of ion pulling and the low-level transverse ion heating followed by mirroring both contribute, I think. Okay, thank you.